Here's an example of how we could build a profit function if we are given a revenue function and a cost function. So suppose we're given the two following functions. Revenue is negative 3q squared plus 250q. We just built that together. And the cost function from earlier in this topic is c of q equals 4.5q plus 750. The profit function is defined to be the revenue function minus the cost function. So to build the profit function, we would simply take the cost function and subtract all of it from the revenue function. In this particular example, it would look something like this. We have the profit function on the left in the blue, and then minus the cost function on the right in green. And now notice that I have put parentheses around the cost function, which is important because you have to subtract the entire cost function. This subtraction symbol right here means that we're taking away the whole thing. We're not just subtracting one piece like the 4.5q, we're subtracting all of it. And so algebraically this means we're going to have to be careful and we're going to have to distribute that negative sign into both terms. When we do that, we get something that looks like this. Notice the negative signs appear for both of the terms in the cost function because the negative sign is being applied or distributed to each of those two terms. So now we just simplify. We have 250q minus 4.5q. That can be simplified a little bit to 245.5q, and then that produces our final profit function. So notice the profit function is also quadratic. The negative 3 in front, because it is negative, tells me that the parabola that represents that quadratic will open downwards. And so let's explore that a little bit more on the next slide. Okay, so this is what the graph of the profit function looks like. If we look carefully at this graph, we will notice that P of Q is right here. It's sort of nestled in the middle of these other two graphs. And it's a parabola like we had said. It opens downwards. And this graph is intended to show you sort of how the profit curve is related to the revenue and to the cost curve. So notice here we have the revenue curve. If you trace that back down, you'll notice that it goes through 0, 0 like we've mentioned before. We also have the cost curve here, which is a line. And so when you combine the revenue and the cost curves through subtraction, you get this profit curve that we have been exploring a little bit, and that's listed here at the top of this slide. Now, one question is, if you look at the profit curve and you trace that curve back down to the vertical axis, which represents dollars of profit, you'll notice that the profit curve starts off below the horizontal or the Q axis. It starts off negative. The question is why? Well, if you go back and you look at the equation, if Q is equal to 0, P evaluated at 0 gives you 0 plus 0 minus 750. And so if you were to do the calculations, you'll notice that when Q is 0, the profit is negative 750, and that corresponds to our fixed cost that we talked about way back when we began to discuss cost functions. So if Q is equal to 0, if no items have been sold and produced, then you still have the startup costs. So your revenue is 0, your cost is 750, so 0 minus 750 gives you your negative profit. So that's what's going on here, and that's why that profit curve starts down there in negative territory. Once we have the profit function, we can define what we'll call the break-even point. On the graph, the break-even point is the first point where the profit function is equal to 0. And graphically what that means is that the vertical value, the y value, the profit value is 0. So the break-even point is essentially when the first time when your revenue, your total revenue, is equal to your total costs. Now think about that for a second. If your revenue and your costs are equal to each other, when you subtract them, you're going to get 0, and that means your profits are 0. So we will define the break-even point to be the first point on the graph where the profits are equal to 0. You'll notice there's another point where profit is equal to 0. Look in the graph and go to the right and you'll see it's close to 80 units on the Q axis. But the one that we will define to be break-even is the first one, the smaller value. So that's our definition, and the way we would then find that point would be to set P equal to 0, and then we could solve that for Q using algebra. So in this example, let's look at what is the break-even point. So as we just said, we would set the profit equal to 0, and so I've done that here. I've set one side of the equation, the profit function, to 0. So it's really just the original profit function. We set it equal to 0. That means it's already in standard form, and so we can go ahead and apply the quadratic formula to it, taking A to be -3, B to be 245.5, and C being -750. And if we were to apply the quadratic formula to this, we're going to get two values. Once again, we have to break those apart separately, calculate a -245.5 plus that root, all divided by -6, and then -245.5 minus that root, all of that divided by -6. And you should check that. You should do that on a calculator and make sure you come up with values that correspond to these. These have been rounded because we're talking about units sold and produced here, so we'll talk about whole units sold and produced. And we get approximately 3 and 79. And again, based on the definition of break-even point, we'll take the smaller one and say that our break-even point is when Q is equal to 3. Once we have all of these algebraic tools at our disposal, we can answer all sorts of questions. We can ask, for example, when are the profits equal to $2,000? For what quantity is that true? And if you look at the graph, you'll see a red dotted line that has been drawn through the value P equals 2,000. And if you look at the graph, you will notice that there are 2 points where that is true, one on the left and one on the right. And again, it's exactly what we've seen before. There are 2 combinations of price and quantity that are going to give you the same profit values. On the left, you have smaller quantities being sold at higher prices. On the right, you have higher quantities being sold but at lower prices. But there are 2 combinations that give you exactly $2,000 of profit. So if we were to solve this algebraically, we would set 2,000 equal to the profit on the left. We have our profit function on the right. And then again, because it is a quadratic, we need to set this equal to 0. So we will just subtract 0 from both sides, and then we will proceed and solve with the quadratic formula. If we were to solve this with the quadratic formula, this is what it would look like. You'll see the first line, we substitute 2,000 for the profit. In the second line, what I've done is I've subtracted 2,000 from both sides of the equation. That leaves me 0 on the left and -2,750 on the right. When I set A, B, and C equal to the appropriate values and run that through the quadratic formula, I get 2 values. Q is approximately 13 and approximately 68 when I round to the nearest unit. If you look at the graph, you'll see red arrows that drop from the curve where the profit is equal to 2,000 down to the horizontal Q axis, and you'll see those correspond to the values Q equals 13 and Q equals 68. So there are 2 quantities where the profits will be $2,000. At 13 items, we charge some price, some higher price than when we sell 68 items. Now, here's something to think about. If you wanted to know what price went with the 13 items and what price went with the 68 items, how would you find those prices?